Hello students, welcome back to next lecture on bifurcations. Today we are going to cover pitchfork bifurcation, slightly different kind of pitchfork bifurcation. Instead of having critical slowing down of decay, we'll have a blow up situation where the value of x will change rapidly once the parameter surpasses the critical value. A typical example of such bifurcation would be subcritical pitchfork bifurcation. Let's get started. So, the example of subcritical pitchfork bifurcation would be the destabilizing term here is x cube. And of course, we know that one of the fixed point is x equal to 0. Let's look at other fixed points. So, the example of subcritical pitchfork bifurcation is dx by dt is equal to rx plus x cube. Now, there are two ways to find the fixed point, which is the first step of finding the kind of bifurcation and trying to understand how the system will behave qualitatively. The second approach would be the graphical approach, and we are going to adopt a graphical approach because we don't want to deal with the nasty cubic equation. So, here we have a line and we have a cube, and we can write this equation as Rx minus x cube. Now, here this becomes our first function, this becomes our second function. We can plot them individually and then see where these curves intersect. So, let's start with plotting them on a phase portrait. So, on x-axis we have x and on y-axis we have dx by dt. By now, you should be quite familiar with how to draw phase portraits. These are not your typical x versus time diagrams. Another thing to note is that here, since we had a plus sign instead of a minus sign, we split that into two minus signs because it is in subtraction that graphical approach to finding fixed points works really well. So, Rx is a straight line, it passes through 0, it has no intercept. Now, the slope of the line Rx will depend upon the sign of R. So, let's say R is greater than 0 to begin with. So, Rx would be a line that looks something like this. The curve minus x cube on the other hand, would behave like so. When x is positive, we'll see a rapid decline, and when x is negative, we'll see a rapid increase. So, when r is greater than 0, we see that these two curves intersect at only one place, and that place is x is equal to 0, which is definitely a fixed point. Now, let's change the value of r. What happens when r is equal to 0? When r is equal to 0, the line coincides with x-axis. And then once again, the only fixed point we have is 0. Now, let's make r less than 0. When r is less than 0, there will come a time when this line will intersect the curve in 3 different places. So, right here we know we are getting a pitchfork bifurcation because x is equal to 0 is always a fixed point as we change the value of r, and then once r goes below 0, once r goes negative, 2 new fixed points arise. So, we have to find this place where we have a saddle node bifurcation kind of phenomena happening, 2 new fixed points are appearing, and in order to find that, if you remember, these are the 2 fixed points we are trying to find, fixed point 1 and fixed point 2. In order to find these, we have to first find the intersection of the line and the curve. And before they intersect, they are tangential to each other, and that's what we are going to figure out before we find the intersection. Graphically, just looking at these phase portraits, we can already begin understanding the stability of the fixed points that we have. Let's start with r greater than 0, where we have only one fixed point. Notice that when x is less than 0, the cube is above the line. When r is greater than 0, only one fixed point. On left hand side, when x is negative, the cube is above the line. Notice the cube is above the line, which means dx by dt will be negative here. When dx by dt is less than 0, x will decrease. So, on x-axis, the x is moving towards left side when x is negative. When x is positive, the line is above the curve. Now, since the line is above the curve, 1 is greater than function 2, which means dx by dt is positive. which means x is increasing. So the flow here would be towards the right side, towards plus infinity. You know now that this fixed point is an unstable fixed point, which we'll denote by an open circle. Now let's look at the second situation when r is equal to 0. Now here, very similar situation on left side when x is negative, the line is below the curve. So curve being x cube here, so the flow will be towards left side. On right side, when x is positive, the line is above the curve. So dx by dt will be positive and the flow will be towards plus infinity. Once again, this is an unstable fixed point. What happens when r dips less than 0 and the line intersects the curve at 3 places? The first fixed point is here, the second fixed point is 0, let's not forget it, and then this positive fixed point will be the third fixed point. Let's try to understand the stability of these 3 fixed points. On the left side of the first fixed point, the curve is above the line. The curve is bigger than line, which means dx by dt is negative, which means the flow is towards left. Between the first and second fixed point, the line is above the curve, which means dx by dt is positive. The flow will be towards plus infinity. Between the second and the third fixed point, the curve, the cube, is above the line, which means dx by dt is negative, flow is towards left side. Now on the right side of the third fixed point, between third fixed point and plus infinity, the line is above the curve, which means dx by dt is positive, x is increasing, the flow is towards plus infinity. Now just by looking at it, you can already understand that the first fixed point is an unstable fixed point. So I'm going to change the color. This we can denote by an open purple circle. The second fixed point, which is 0, is a stable fixed point. So we will denote it by a closed circle. The third fixed point is again an unstable fixed point, open circle. So even without finding out the exact places where these curves intersect, we already know how the system is going to behave. Now, subcritical bifurcation, things tend to blow up. What happens is, because x cube here is the destabilizing factor, as x increases, the destabilizing factor x cube increases rapidly. So when the object moves away from the unstable fixed point, then the velocity, the rate at which it moves, increases rapidly. And what we see in this kind of situation is informally referred to as blow up, where things explode, the values increase very fast. So if we are talking about sudden increase in some environmental parameter, for example, let's say sudden increase in population of insects, sudden increase in the population of malaria carrying mosquitoes, or number of incidences of a particular disease, they are having something very similar happening. The destabilizing factor is positive and things are increasing very rapidly. Now these were the different kinds of bifurcation that I covered. Now I'm going to give you an example where we suspect that there's some kind of bifurcation happening, and we want to figure out what kind of bifurcation and what this bifurcation analysis tells us about the system. So we'll start with a very simple system. The example that I'm going to cover now is a very simple example. Let's say we are talking about a lake, right? So we have a lake and it's a clean lake, so it's not undergoing eutrophication. There are fishes that are thriving in the lake, and we are going to model the number of fishes in the lake, how they are growing, and what happens to them when we start fishing them. So this is a fishery model. Let's call it fishing model. The model is not fishing. So here I want to give you an insight into how we design models, and we are going to go about this in detail later on. Now in the lake we have fishes. We have studied 3 different growth models so far: the exponential growth, the logistic growth, and the Gompertz model. The number of fishes in the lake we know will depend upon 2 very important things. First is the rate at which fishes biologically multiply, the amount of time they need to multiply, which is the doubling time or multiplying time. The other thing is the resource limitation that they'll face in the lake. It seems that logistic equation for the growth of fishes would be a very nice model. So we can say that the major driving factors. So remember, in the introductory lecture I told you, first we write a conceptual model. So let's write a conceptual model. the rate at which the number of fishes f will change will depend upon two things. First, positive, the rate at which fishes are growing. At what rate are they? What is their growth rate? Minus the rate at which they are dying from natural reasons like aging, and minus the rate at which we are fishing them out of the lake. Right? This is our conceptual model. You see, plus means this particular factor, which is the biological replication, is contributing to increase in the df by dt. Minus means it is causing a decrease in df by dt, f being the number of fishes. Now, this growth model that we are going to use, which is logistic growth model, accounts for both the net growth rate, which means growth minus the natural death rate. So, we can write this as df by dt is equal to rf1 minus f by k. R here is the biological growth rate, K here is the carrying capacity of the lake, which depends upon the lake. So, it is the intrinsic variable of the lake, minus the rate at which you are fishing, let us call it F, H, not F, let us call it H. Alrighty, so we have this model. Now, remember, the first step was write the conceptual model. The second step is write the mathematical version of it. Right? Now, we have this model and we are going to see if this model has some bifurcation happening. Now, why is it important to understand if, or to figure out if this model undergoes bifurcation? In a big enough lake with large enough number of fishes, if we continue fishing up to some limit, it would be a sustainable fishing practice. We will not run out of fishes, sustainable from human perspective. However, if the lake does not have enough number of fishes and we are fishing far more rapidly than the lake can sustain, the number of fishes can sustain the fishing practice, then we will run out of the fishes. So, we already know that depending upon how this particular parameter changes, parameter h, we already know that the outcomes would be very different. So, we already know that as one parameter changes, the outcome is changing. So, there is a very good reason to suspect there is bifurcation happening. Now, here we have three variables r, k and h, and if we are going to do bifurcation analyses for them, we have to vary each variable. Now, this is where I want to introduce you to non-dimensionalizing the system. This is called dimensional scaling and analysis. What we are going to do is we are going to minimize the number of parameters, and here it's for a very simple reason, because I only want to look at h and I can keep r and k constant and just do bifurcation analysis for h. But there is another reason for it. Dimensional scaling and analysis is extremely important in environmental models because, as I mentioned in the introductory lecture, environmental phenomena happen at a wide range of time scale. So, there are few things that will happen very rapidly. For example, certain fishes might reproduce very rapidly, some other fishes might take a very long time to reproduce. On the other hand, fishing can be a daily phenomena, can be one season per year phenomena, a seasonal phenomena, or it could be an occasional thing that humans practice maybe once a year, maybe during a particular summer break or spring break. So, it is quite possible that the time scale at which the fishes are replicating and the time scale at which we are fishing, the humans are fishing the fishes, are very different. In fishing it is not so apparent, but it is more apparent in for example, in case of forestry. So, if instead of being a fishing model, this was a model for the number of trees in the forest, then the trees will take many decades to grow to full size trees, but cutting the trees can be done very rapidly in a single day. We can cut many trees which have taken decades to grow. So, in one case we are looking at a phenomena that is happening on scale of hours, which is cutting the tree. On the other hand, we are looking at a phenomenon that takes many decades. What dimensional scaling does is it non-dimensionalizes each parameter in each variable in your system. So, now there are no units once we are done with dimensional scaling. There are no units in your system and we are dealing with only non-dimensional parameters. So, let us figure it out. Let us see how to do non-dimensional scaling of this particular model. Now what we want to do is we want to non-dimensionalize f. F is our variable for number of fishes, and we want to non-dimensionalize t, which is time, because time has units. We want to have a non-dimensional parameter, a variable representing time. So a very simple thing that we can do is declare f by k as a new variable. So let's say f by k is equal to small f. So now we have df is equal to k small df. Yeah. So replace this here and we get. So we are going to substitute this in this particular system. So df by dt will become this is equal to r So now we have converted, we have non-dimensionalized one variable, which is the number of fishes. Now we want to non-dimensionalize time. So what we can do is we can, okay, let's look at left hand side. The unit on the left hand side is df is number of fishes, dt is the unit of time. So and k has the unit of fishes. So now what we can do is take k on the right hand side and we are left with df by dt is equal to r f 1 minus f minus h by k. So now let's look at each term and see what their units are. On left hand side we have df by dt, which is f is unitless, t is time. So here the unit is per time. On right hand side in the first term, f into 1 minus f is unitless because our small letter f is unitless variable. R on the other hand has a unit which is per time, and h by k, h is the rate at which we are fishing. If we look at the unit of h from here, the original model, h is number of fishes per time divided by k, which is number of fishes, we are left with per time. So the only unit we have left in our system now is per time. So it is time to non-dimensionalize t. So in order to do that, what we can do is we can define a new time tau, and what we can do is we can define rt as the new tau. This is a non-dimensionalized time, and we are going to interpret why rt, why did we choose f by k. I'm getting there, don't worry. So if rt is equal to tau, r dt is equal to d tau, and we can substitute this here. Okay, now our system has no variable that has unit. Each of the cluster of the parameters in variable is unitless, but we still have r, h and k which have units, and we want to get rid of them too. We have parameters that have units. Variables, we are done. So what we can do is we can take r to the right hand side and we are left with df by d tau is equal to f into 1 minus f minus h by r k. So now once again we have all the parts of this model are unitless except for this one. So now time to convert this one into a unitless parameter. So let me write down fresh what we have now. Okay, we can define a new parameter small h, which is equal to h by kr. So this is a new fishing parameter which is dimensionless, and we can substitute here. So we have df by d tau is equal to f 1 minus f minus small h. So now we have a non-dimensionalized system. None of the parameters and variables have any unit, and my intention was to reduce the number of parameters, and I actually have only one parameter left, which is small h. Now we can go ahead and do bifurcation analyses. But before we get there, I want to take some time to explain to you the substitutions we have done. They're not just random, they have meaning. So let's start with this one first. The new fishing parameter, which is h by kr. Let's try to understand. H is the rate at which we are fishing. Fishing rate. Divided by k, which is the maximum amount of fishes that lake can hold. maximum number of fishes that lake can hold, divided by rate at which they are growing, growth rate of fishes. So right here you can see that the new parameter small alphabet, a small letter h that we have introduced actually compares the rate at which we are removing the fish from the lake to the amount of fishes that in best case scenario we can expect in our lake. So if h is very high, if the rate at which we are fishing is much higher than the maximum amount of fishes that the lake can bear and the growth rate of fishes, then we already know that it's not going to be a sustainable practice. On the other hand, if h is very low, then we know that we are fishing at a rate which is much lower than the capacity of doing sustainable fishing in this particular lake. Okay, now let's look at another variable that we introduced, which was small f is equal to number of fishes divided by k, carrying capacity. If you remember from our lecture on logistic growth rate, this is also a very important variable that we have introduced. It is telling us the ratio of the number of fishes in the lake to the carrying capacity. So we know if f is greater than 1, number of fishes even without fishing is going to decline. They are going to come down to carrying capacity. If f is much smaller than 1, we are going to see an exponential increase in the number of fishes. If f is nearly 1, then we know that the number of fishes are at carrying capacity. So again, this is also a very informative variable that we have introduced. It tells us how close or how far the number of fishes are to the carrying capacity. Now the carrying capacity here is calculated in absence of fishing, just so that you know. The third variable that we introduced was RT is equal to tau. We introduced a dimensionless unit of time which is equal to the rate at which things are growing into time. Now if you look at rate, the unit of rate here is per time. So let's say if the rate of, if the R value is, let's say 2, yeah, I'm taking a random number 2. What it is telling me is that at 1/2 units of time, replication happens. So the higher the R, the faster the replication happens, right? R is 1 by time. So 1 by R will give me the replication time for the species. And R gives me growth time. So when I'm multiplying R with time, I'm finding out, basically what I'm doing is, so 1 by R is replication time, let's call it rep time, rep t. So we can say R is equal to 1 by rep t. So RT, which is our new variable tau, is equal to time into 1 by rep time. So we are looking at how many replication times have passed. So for example, for a particular bacterial species, replication time is 20 minutes. Every 20 minutes, the cell becomes mature and splits into daughter cells, and let's say 2 hours have passed. So we know then if 2 hours have passed, then 6 replication times have passed. So tau is giving us idea of how many replication times have passed, have elapsed. So again, each of the variables that we have defined have meaning. When you do dimensional scaling of your system, it is very important to pause and look at your system and try to see what you're doing. Alrighty, time for bifurcation analysis. For bifurcation analysis, the first step is to understand how the system behaves, what the fixed points are. So let's proceed. The fixed point of this system, we can open up the brackets and we have f minus f square minus h. So we can, again, I am a fan of graphical approach, so I'm going to use the graphical approach to find the fixed points. We have f minus h minus f square, we have a line and we have a curve, and they're separated by minus. Life is easy here. So let's plot it, the phase portrait. df by d tau. In your exam, do not make mistake of writing df by dt. I'll be very careful that you get your alphabets right. And here we have f, alright. So let's plot f minus h. We'll assume that h is greater than 0. So f minus h is a line with negative intercept magnitude h, and the slope of this line would be 1. So it will look like this being h. F squared is a curve that looks like this. Okay. So, when h is greater than 0, this is how the line looks like. Now, let us start varying h. So, what we are going to do is start reducing the value of h. So, x square remains, f square remains here constant, there is no parameter, we are not changing it, we are only changing the value of h. So, what will happen is that h will become closer and closer until at one particular time it will be tangential to this line. So, here this is your value of h. We want to find out this point because this is the critical value of h, h critical, at which a new fixed point appears. This is your fixed point. So, let us look at the stability of this new fixed point that has appeared. On left side, the curve is above the line. So, df by d tau would be negative, f is reducing. On the right hand side of the curve, right hand side of the fixed point, the curve is above the line, which again means df by d tau is negative, f is reducing. So, we see that on the right side, this fixed point is stable, on the left side, this fixed point is not stable. Let me redraw this. In your exam, final exam, if you choose to write it, I will pay particular attention to how you show me graphically the stability of the fixed point. There you are. Now, let us keep reducing h. There will come a time when this line will cut the curve in two different places, giving us two fixed points, fixed point 1 and fixed point 2. Let us look at stability of these fixed points. On left hand side of the first fixed point, the curve is above the line, which means df by d tau is going to be negative, the flow is going to be towards minus infinity. Between the two fixed points, the line is above the curve, the first equation has higher value than the second equation, df by d tau is going to be positive, the flow is going to be towards right side. On right side of the second fixed point, the curve is above the line, df by d tau is going to be negative, the flow is going to be towards minus infinity. Now, just by looking at this graph, you can tell that the first fixed point is an unstable fixed point because on the either directions, on the either side of the fixed point, the flow is moving away from it. The second fixed point is a stable fixed point because the flow is moving towards this fixed point. Okay, pause this video after this and figure out what kind of bifurcation is this. I hope that you did pause the video and you guessed it correctly. This is a fixed point. This is the kind of bifurcation where two new fixed points appear out of blue sky. This is the saddle node bifurcation. So, now you know how to identify the kind of bifurcation it is. In the next class, I will show you how to interpret this example, how to use it to inform you practical questions, in this case about fishery. See you in the next lecture.